All right, let's dive right into your high-speed review of oceanography. This is all about sharpening your knowledge for the CSIR exam. We're going to move fast through the core concepts, hitting all the key takeaways you'll need. Let's get going.
You know, this quote from astronaut Loren Shriver really hits the nail on the head. Our planet is a water world first and foremost, and understanding this huge interconnected system is exactly what oceanography is all about. This perspective is absolutely crucial for grasping the scale of what we're about to cover.
Okay, so first up, we're going to start at the very bottom. The geology of the ocean floor. The shape of these basins, how they move, it controls everything from currents to where life thrives. So understanding this is our first critical step.
So, how do we know the continents weren't always where they are now? This is the question that really kicked off a whole revolution in Earth sciences. I mean, you look at a map, you see how they fit together, you find matching fossils and rocks. It all points to one thing: the continents are on the move.
And the answer, of course, is the theory of plate tectonics. It's the bedrock of modern geology. This builds on Alfred Wegener's idea of that ancient supercontinent Pangaea, and it finally gives us the how. It explains how our continents have drifted to where they are today. So what's the engine driving all of this? Well, it really comes down to a fundamental difference between two types of crust. As you can see, the oceanic crust is made of dense basalt. It's thinner but heavier. The continental crust is thicker but lighter granite. So the dense oceanic crust naturally wants to sink, or subduct, under the lighter continental crust. That simple density difference? That's an absolutely critical concept to lock in.
So these plates are interacting in three basic ways. At divergent boundaries, they're pulling apart. Think of the mid-ocean ridges. That's where new seafloor is literally being born. At convergent boundaries, they're smashing together, creating deep trenches and volcanoes. And at transform boundaries, they're just sliding past each other, like the famous San Andreas Fault.
All right, we've talked about the container. Now let's talk about what's in it. The chemistry and physics of seawater itself are what make all life in the ocean, and life on Earth for that matter, possible.
You might think it's just water, right? But ocean water has this incredible set of properties. Its chemical structure is the key to everything. It's what makes it a life-sustaining, climate-regulating powerhouse.
Okay, here are the crucial takeaways for water. First, it's a polar molecule, which makes it a universal solvent. It can dissolve all sorts of salts and nutrients. Second, its high heat capacity is huge. The ocean is basically a giant heat battery, absorbing and releasing energy that regulates our entire planet's climate. And third, the fact that ice floats is so important for life in the polar regions.
And of course, when you talk about seawater, you gotta talk about salinity. It's just the measure of its saltiness. And that 3.5% figure? Yeah, you're gonna want to remember that one. That's the global average, about 35 parts per thousand.
It's all about a simple balance, really. Think of it this way. Anything that removes fresh water, like evaporation or the forming of sea ice, is going to make the remaining water saltier. It increases salinity. And on the flip side, anything that adds fresh water, like rain, snow, or rivers flowing into the sea, is going to dilute it and decrease salinity. Okay, let's get things moving. The ocean isn't just a big, still pool of water. No way. It's a dynamic system of currents, like a massive global conveyor belt, transporting heat, nutrients, and life all around the globe.
If there's one concept you absolutely have to understand for large-scale currents, it's the Coriolis effect. Now, it's not a real force, it's an apparent one. It's all because we're on a spinning planet.
And here's the rule of thumb you need to memorize. In the northern hemisphere, things get deflected to the right. In the southern hemisphere, they get deflected to the left. This applies to everything that moves over a long distance, especially wind and water. It's a key principle.
So, what happens when you mix those big global winds with the Coriolis effect? You get these massive circular currents called gyres. The 5 major subtropical gyres in the North and South Pacific, North and South Atlantic, and the Indian Ocean, these are the giants that totally dominate surface circulation.
Another huge process in ocean motion is something called upwelling. This happens when wind pushes surface water away from the coast, and that allows deep, cold, nutrient-packed water to rise up to the surface. It's like fertilizing the ocean, which is why you see these massive plankton blooms that create some of the world's best fishing spots, like off the coast of Peru.
So, we've set the stage. The geology, the water, the currents. Now let's bring on the actors. The incredible diversity of life in the ocean, from the teeniest microbes to the biggest whales.
You know, at the very highest level of classification, all life, marine life included, fits into these three domains. What's important to remember is that the ocean isn't just full of fish and seaweed. It's got representatives from every single major branch on the tree of life.
A great way to classify marine life is by how they live. First up, we've got the plankton. These guys are the floaters. They just drift with the currents. You've got phytoplankton, which are basically microscopic plants, and they form the base of the whole marine food web. And then you have zooplankton, the tiny animals that munch on them.
Then you have the nekton. These are the swimmers. Unlike plankton, they can actually move on their own against the current. This group includes pretty much everything you'd picture: fish, squid, turtles, and, of course, whales.
And last but not least, we have the benthos. These are the bottom dwellers. They live on, in, or are attached to the seafloor. It's an incredibly diverse group. Everything from corals and sponges just stuck there to crabs and sea stars crawling around.
Okay, for our final section, we need to talk about something really critical: the human-ocean connection, and frankly, our accelerating impact on this massive, vital system.
Just look at this number. It's staggering. An estimated 5.8 million metric tons of trash hitting the oceans every single year. This is a classic example of what's called non-point source pollution, trash from land that just finds its way to the sea, and it has absolutely devastating effects.
And it's not just the plastic bottles you can see. There's an invisible threat too, and it works through a nasty process called biomagnification. Here's how it goes down. Toxins like DDT get into the environment. They're absorbed by the tiny phytoplankton at the bottom of the food web. Then, as bigger things eat the smaller things, those toxins get more and more concentrated up the chain. So the animals at the top, like tuna, dolphins, and even us, end up with the highest, most dangerous levels.
Another massive human impact is ocean acidification. Look, it's pretty straightforward. The ocean soaks up about a quarter of the CO2 we pump out. When CO2 mixes with water, it forms carbonic acid, which lowers the ocean's pH. People call it the osteoporosis of the sea because it makes it so much harder for animals like corals and clams to build their shells.
And that really brings us to the final crucial question to think about. The ocean gave us life. What are we giving back? The health of the ocean is completely tied to the health of our planet and ourselves. Understanding this stuff isn't just for an exam. It's about our responsibility. That's a powerful idea to leave you with.